Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at optimization. So optimization, you're finding like an optimal solution. We're finding either the lowest possible or the highest possible value of something. Now, we learned when we were doing curve sketching that maximum or minimum values of a function always occur where the first derivative is equal to 0. So the process here is actually pretty simple. Either we're going to be given a function or we need to find a function, and then we simply need to differentiate it and find where its first derivative is equal to 0. So let's look at this question. Box to be made from a 1 by 1 meter square of cardboard with squares cut out from each corner. Calculate its maximum possible volume. Now, we're not given here a function for the volume of the box, so we need to find one. So let's start by drawing our 1 by 1 meter square of cardboard that has squares cut out from each of its corners. So the thing we don't know here that we really do need to know is how long these squares are. What's the side lengths of these squares? So I'm going to call that x. What we need to do is find an expression for the volume of the box in terms of x. So what's going to happen is these squares are cut out and then we fold up here. So we're going to fold like along this line to make a 3D box. So the base of the box is going to be this square here. So what are its dimensions? Well, if it's 1 all the way across here, and this is x and x, then the dimensions must be 1 minus 2x, and similarly 1 minus 2x. So the box has a base that's a square with side length 1 minus 2x. This x will actually be the height of the box when you fold it. So whatever value that is, if it's 30 centimeters, then the box will be 30 centimeters tall. So it turns out that the volume of this box is going to be length, width, and height multiplied together. So the width and length are both 1 minus 2x, so I can write it like this. So if I want to find out where this is a maximum, I need to differentiate this function. So I can use the product rule for this, or I can expand this. Either way doesn't matter. So I'm going to use the product rule. So product rule tells me the derivative of v will be derivative of the first, which is 1, times by the second. And then product rule is always plus. So it'll be the first times derivative of the second. So the derivative of this here, I'm going to use the chain rule. I move the power to the front, decrease the power by 1, but I also need to remember to multiply by the derivative of what's inside. And of course, the derivative of negative 2x is just negative 2. So I might make this easier on myself by factorizing, because both this and this have a factor of 1 minus 2x. So if we move 1 minus 2x to the front, I need to multiply by another 1 minus 2x to get this thing here, and I need to multiply by negative 4x to get that one there. So the derivative here is 1 minus 2x, and in the second bracket, it's actually 1 minus 6x. So we have two possible solutions here if the first derivative is equal to 0. Either 1 minus 2x is equal to 0, so that would mean that x is equal to positive a half, or if 1 minus 6x equals 0, x would equal a sixth. So we know that one of these is going to give the side length of the squares cut out that will yield the maximum volume, but we don't know which one's which. So let's substitute each of these into the original function. Now it turns out if x equals a half, this will mean v equals a half times 0. This will actually yield a box whose volume is 0. And of course, if this is a half and this is a half, you've got nothing left for the width of the box. On the other hand, if I substitute x equals 1/6 into this expression here, we actually get about 0.074, and because everything was in meters, the volume would be in meters cubed. So clearly this is the higher value. It will yield the maximum. It may look small, but it's actually 74,000 centimeters cubed. And then we're done. Let's look at a problem now involving triangles. So a right angled triangle has hypotenuse 20 centimeters. Calculate its maximum possible area. So again, because we're finding a maximum here, we need a function to differentiate, and then we find where the derivative is equal to 0. So in order to come up with this function, let's start by drawing a diagram. So we have a right angled triangle, hypotenuse here is 20. We need to find a function for the area of this. Now the area is just these two multiplied together divided by 2. Problem is, I don't want to call these x and y because we don't yet know how to differentiate a function that has two different variables. What I want to do is write each of these sides both in terms of the same variable. Turns out I can do that quite simply. See, if I call this angle here theta, then we know that adjacent over 20 is cos theta. So what we can do is rewrite this side here as 20 cos theta. And similarly, this side here will be 20 sine theta. So that helps because I've written both sides in terms of the same thing here, theta, same variable. So the area of this is just going to be 20 cos theta times 20 sine theta. Now, because it's a triangle, half a rectangle, I need to divide base times height by 2. So just simplifying that, 20 times 20 divided by 2 is 200. So 200 times cos theta sine theta. That is my function for the area. So let's differentiate it so we can find where it is maximized. So we can use here the product rule. I'll just put the 200 out the front. Derivative of cos theta is negative sine theta. So we go derivative of the first times the second. Negative sine theta times sine theta, I can just write like this. And then it's plus cos theta, so the first times the derivative of the second. So I just get cos theta times cos theta, and I'll just write that as cos squared theta. So we want this thing here to equal 0. Of course, if a dash equals 0, 200 doesn't equal 0. So what we have is that cos squared theta equals sine squared theta. That's the only way that this is going to equal 0. So we have cos squared theta equals sine squared theta. Now, we know that these both have to be positive. Why is that? Because theta has to be less than 90 degrees because of this 90-degree angle. So we know from the unit circle in the first quadrant, both sine theta and cos theta are positive. So because their squares are equal and both are positive, we're really looking to find where sine theta is equal to cos theta. So you might know the answer to this off the top of your head. If you don't, you can divide by cos theta. You get tan theta equals 1, and theta equals 45 degrees or pi on 4 radians. So if it was pi on 4 radians or 45 degrees, this would be 20 over cos theta. It would be 20 times 1 on root 2. This would be 20 times 1 on root 2. So the maximum area would be 20 times 1 on root 2. That's 20 cos 45. Now we square it, timesing it by 20 sine 45, which is also 1 on root 2. And then we need to divide by 2. Putting that in our calculator, we get 100. The maximum possible area is 100 centimeters squared, and it happens when this right-angled triangle is isosceles. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.